In this video, we are going to review the factoring that you learned in Algebra 1. So today we are going to factor using several different methods for polynomials. We are going to look at taking out a greatest common factor, or GCF. We are going to factor trinomials where the lead coefficient is 1. We are going to look at some special trinomials where we are looking at perfect square trinomials and also the difference of two perfect squares. And then we are going to factor by using a method called grouping. And this is going to be used for trinomials where you have a lead coefficient that is not 1. So usually it's a number whose absolute value is greater than 1, 2 or 3, that kind of thing. Okay, so let's look at the first method. The first method is finding the greatest common factor, or GCF. And for this method, we are looking for terms that the two terms have in common, so we can apply kind of a reverse distributive property idea to factor it out. So if you look at this first example, both the first term and the second term of this expression are divisible by 3. So that is my GCF. I'm going to factor out that GCF and write s squared minus, and 24 divided by 3 is 8. So that is 8. I've factored out the greatest common factor. So let's look at another one where we're just looking at pulling out that GCF. If we look at these two terms, you'll notice that both of the numbers 16 and 12 are divisible by 4. So we're going to factor out a GCF that has a 4 in it. But these also both have the variable n in them, at least one. So because this one has 1, this one has 2 n's, we're going to factor out one of them because we can only take out what each one has. If this one doesn't have 2, then I can't take out 2 because this is n squared and this is only n to the first power. I also want to point out here that the lead coefficient, meaning the first term that has the largest order or power, has a negative sign here. Whenever the lead coefficient is negative in your factoring, I also want you to factor out that negative sign. So we're going to factor out the GCF of negative 4 times n. So let's take that out. When we remove the negative 4, negative 16 divided by negative 4 is positive 4. And n squared, whoops, we're taking out that n too, n squared divided by n leaves us with just that one other n inside. The second piece is going to leave us with negative 3, because positive 12 divided by negative 4 is negative 3, and then this n got factored out, so there's no variable left here. Now, with all factoring, GCF and the other methods, you can always check your work, because you can, in this case, take the distributive property and distribute the GCF back in to the equation or the expression, and you should get the problem that you started with. If you distribute it back in and you don't get the problem back, that means you've made a mistake somewhere and you should go back and look for that mistake. Let's look at the second method for factoring. For the second method, we are going to be factoring trinomials, and this time the leading coefficient, that's the a value that's out front, is going to be equal to 1. So let's look at how to do this. If you have an equation that's written in standard form, like it is here, we first want to make sure that yes, indeed, this lead coefficient is 1. That means we can use this method. The first step is to list all possible pairs of constants where we can get the c value, negative 32. So I'm going to write a 32 over here, and I'm going to list out all the things that I can multiply together to get 32. I could do 1 times 32. I could do 2 times 16. 32 is not divisible by 3, so I'm not going to write that, but then I am going to write 4 times 8. So now after we have our list of possibilities, we need to decide on a sign based on the sign of the c value that we just used to list these out. If this is a minus sign, a negative sign, that means when we do our factoring in a moment, the signs of these two factors are going to be different signs. One is going to be positive and one is going to be negative. So I need to choose a set of factors, a pair of factors that multiply together to get 32. That's any of these, but they also have to add together using different signs to get negative 14. So the one that I see jumping out at me is 16 and 2, because if I need to get negative 14, that is the same as negative 16 plus 2. That's negative 14. So I'm going to take this negative 16 and I'm going to put it in the one that I've already drawn my minus sign with, and this positive 2, I'm going to put it in the one that has my positive. To get x squared, you just do x times x. And that will always be the case in these where the lead coefficient is 1. The first term will be x in both of the factors. So looking at what you've got here, you have, if you FOIL it back together to check your work, x times x is x squared. If we distribute this x to the negative 16, that's negative 16x. The inner is plus 2x, and the last is negative 32. So that simplifies because these are like terms, so I'm going to combine them. 2x squared minus 14x minus 32. That was the original problem, which means when I did my distributing to check, everything worked out. So again, to recap here, you're going to list all of the possibilities. You're going to decide on the sign of your two factors, and you're going to choose the set of factors that add up to your middle term, b. You write it as your product, and then you check by foiling or distributing. Okay, so let's look at another example of this one, because this is a fair number of steps that you have to remember to get through. So looking at this first one, the first step is to list out all of the factors of the C term, 36. So let's write our 36 over here in the margin. You can multiply 1 times 36 to get 36. You can do 2 times 18, 3 times 12, 4 times 9, and 6 times 6. So all of those multiply together to get 36. When I write my two factors here to get the x squared, that's just going to be x times x. Now I need to choose the sign that goes here so that I know which one of these from my list to pick. Because this is a minus sign, that means in my factors I'm going to have opposite signs, or different signs, one positive and one negative. So now let's see what we can do with this. We need to add together to get positive 5 using one of these pairs. I see 4 times 9, and I like that because 9 minus 4 is equal to positive 5. So those use different signs, positive 9 and negative 4, and they add together to get 5, multiply together to get 36. So let's stick those two numbers in. The 9 is the positive one, so it's going to go where I've already drawn my plus sign. The 4 is the negative one, so it's going to go where I put my minus sign already. And that is my answer. I can distribute these back together, and that should give me x squared plus 5x minus 36. So to check that, if I do x times x, that's x squared. For my outer piece, or the second piece of the distributing, that's minus 4x. This inner piece is plus 9x, and the last piece is negative 36. These like terms get combined, so that is x squared plus 5x minus 36. That was my original problem, so it checks. Okay, let's look at some of the special factoring that we're able to do. If you have a trinomial where both the first term and the last term are perfect squares, there is a special pattern for how to factor these. You can factor these using the method we just talked about, though if you recognize this pattern, it will save you a little bit of time. So this method says, and I'm going to talk through this first example with it because I think it will make this symbolic representation easier to understand. The property says that if you have a perfect square trinomial, this first term is going to, whatever the square root of it is, x squared is the same thing as x times x, goes in that first one. The c term, 64, that's 8 squared, which means that the base, 8, is going to be in the second spot for each of the factors, because 8 times 8 is 64. And then because this is the positive sign, that means I have to do the same sign in both of these here. To add them together to get negative 16, they both have to be negative, because negative 8 minus 8 is negative 16. So look at what has happened here. I have two factors that match exactly. That is x minus 8 quantity squared. And this trick will always be true for perfect square trinomials. If you can take the square root of the first number, or the first term, because it's a perfect number, and you can take the square root of the last term, the c term, that means this is a perfect square trinomial, so you can write those two bases with whichever sign is required to get this same sign in both of them, and in this case a negative sign at the end. That quantity squared is your answer. So let's look at another one of these. When you look at this first term, 4x squared, I see 2 squared and x squared, so that quantity 2x squared. That's a perfect number. I can take the square root of it, and that base 2x is what's left. The 9 is 3 squared. So because both of those are perfect squares, we can use this method where the first term in both of the factors is going to be whatever the first base is, 2x. The second term is going to be whatever the c base is, 3. And then because this says that my signs have to be the same and I have to get positive 12, they're both going to be plus signs. So 2x plus 3 quantity squared is the fully factored version of this expression. The other example we are going to look at, or the other method we're going to look at of a very special type of factoring is when you have a difference of two perfect squares. Now I do need to emphasize a couple of things here. First, this is a binomial, meaning that there are two terms, not three in the original problem. Second, super important, this is a difference, meaning that this must be subtraction. This perfect square idea only works if it is subtraction for this method. So let's look at what happens here to get the symbolic representation. If you have x squared minus 25, these are both perfect numbers. X squared is a perfect number and 5 squared is a perfect number. So according to this method, the two bases are going to be my first and last term in both of my factors, and because this is a minus sign in between the x squared and the 25, that means we're going to have different signs in our two factors. One's going to be positive, one's going to be negative. This will always work out if you have a difference of two perfect square numbers. So that's my factored piece there. Let's look at several more of these. This next one is a little bit harder to see, but do you see that you have nice perfect squares here? 49 is 7 squared, 121 is 11 squared. That means that this is equivalent to 7x quantity squared minus 11 squared. These are both perfect square numbers, and there is a minus sign in between, which means you have a subtraction or a difference. So we can use this method to factor. The first term in both factors is the first base. The second term in the both factors is the second base. And then because it's a minus sign, they have opposite signs in between. So you get 7x plus 11 times 7x minus 11. Remember, you can always distribute these back together or FOIL to check to make sure that you did that correctly. Okay, let's look at this next one. It's a little different. Do you notice anything about it? You have x squared, which is a perfect square. You have 100, which is a perfect square. It's 10 squared. But what do you see in the center of these? Do you see this plus sign? That means you cannot use this method. It is not a difference of two perfect squares. These also have the special attribute of being what's called a prime polynomial. These polynomials cannot be factored. No matter what you try, any method, it's not going to work for this one. So you can write prime polynomial. Prime meaning that there are no factors. And this will be true anytime you have a sum of perfect squares. You cannot factor that polynomial. Let's look at another one that is, again, a difference of two perfect squares. Now you see the x to the 6th and you go, that's not really a perfect square, Miss Yee. That's a 6, not a 2. But if I use the exponent rules to write this as x to the 3rd raised to the 2nd power, because 3 times 2 is 6 using the power raised to a power exponent rule, now I have a quantity that is squared, and that means it's a perfect square. How do you think we should change this y to the 4th if we need it to be squared in the end? What is the base here? Did you say y to the 2nd power because 2 times 2 is 4? If so, that was right. So let's look at this now. Let's write out our two factors. The first base is x to the 3rd. So that's going to go in the first slot for each of the factors. The second base is y squared. So that's going to go in the second slot for each factor. And then because this is a difference, that means I can factor it. That's why I'm doing this. One's positive, one's a minus sign. So that's my factored version. If I distribute these back together or FOIL, they are going to give me back this original problem when I simplify and combine like terms. Okay, we have one last method to look at today. This method is for when you're factoring trinomials where the leading coefficient, meaning that number out in the very front with the highest exponent term, is not equal to 1. You are also going to hear this method called factoring by grouping. That's the term I'm going to probably end up using most often in class when we talk about this. So know that when we factor by grouping, I'm talking about factoring most often when the lead coefficient is not equal to 1. So if you look at this example, this first problem, notice that there's a 2 out here where the a is. That means if there's not a GCF, then I am going to have to use this method of grouping. There is no GCF because 7 is an odd number, so I can't pull out a GCF of 2, which means I'm stuck with it. So let's go through these steps here. The first step is to multiply a times c. So I'm going to take this a value, I'm going to take that c value and multiply them together. And I'm going to do this over here in the margin because we're going to be using this other space for some of our other work. So 2 times 6 is 12. After you have your minimize that. After you have your a times c, then we're going to do what we were doing before. We're going to list out all of the possible factor combinations. So we have 1 times 12, 2 times 6, and 3 times 4 as all of our possibilities. We are again going to decide on what kind of sign we should use. Because this is a positive sign, that means we're going to use the same sign for both of our pieces. And we're looking at choosing one of these that add to 7, just like we were before. So to get to 7, I see 3 plus 4, using the same sign, positive 3 plus 4. So we're going to use that set of factors. Now here's where the steps get different. For step number 5, we're going to rewrite the middle term, the b term, using the two factors that we just found, 3 and 4. So I'm going to rewrite this expression, and this part that I've double underlined here, I'm going to write it as plus 3x plus 4x here. All right, so let's see, we've got 2x squared plus, and I'm actually going to switch that order, you'll see why in just a moment, plus 3x plus 6. So notice here that I have written 7x as 4x plus 3x. And the next step is that we're going to factor by grouping. We're going to group these first two terms together. We're going to group the last two terms together and factor a GCF out of each one individually. And this is why it's called factoring by grouping. So if you look just at these first two terms, 2x squared plus 4x, do you see that they both have a GCF or a factor of 2x? If I look just at this part, I can take out the 2x, and that leaves me with x plus 2 in that particular group. I've just taken out the GCF from the first two terms. Let's look at the second two terms now, or the last two terms. We're going to do the same thing, looking just at these. What can we take out as a GCF from 3x plus 6? It has a GCF of 3, and that leaves me inside with x plus 2. Okay, so notice number one that this sign in between, that plus sign, I still wrote it there. Don't lose that sign. And do you see now that the leftovers from taking out both of the GCFs match? That's good, because what that means is that we can take out another GCF, because this term and this term both have something in common, x plus 2. So I'm going to write x plus 2, and then my second factor is going to be these original GCFs that I found, 2x plus 3. I can FOIL these two back together to check, and it's going to give me my original problem. So let's look at that. X times 2x is 2x squared. The outside, or second piece of distribution, is plus 3x. The next distribution is plus 4x. And the last part of our distribution, 2 times 3 is 6. So that gives me 2x squared plus 7x plus 6. That was my original problem, which means this checks. So again, just take you through these steps because there are a bunch of them. You multiply a times c together first and list out all the factors, just like you do when the leading coefficient is 1. But then when you make your choice about which one to use, you're going to substitute it in for whatever the middle term is, the linear term. So instead of 7x, I wrote 4x plus 3x. Why do you suppose that I put the 4x over on the left and the 3x over on the right? Did you notice that on my next step I had to factor out a GCF? I placed these so that my even numbers were together because they have a GCF of 2, and I placed my 3 and my 6 together because they have a GCF of 3. You can write these two numbers that you're choosing over here in either order, whichever makes factoring out the GCF easier. It actually doesn't matter which way you do it, though I like to put the ones with nice GCFs together. You could write these numbers as 2x squared plus 3x plus 4x plus 6, and that would also give you the same ultimate answer down here. So again, after you rewrite that number, you factor out the GCF from both. Your leftovers are one of your factors, so you write it down. And then the GCFs are your other factor, so you write it down as the second factor. Don't forget to check your work by foiling things back together or distributing. Okay, so those are 5 different methods for factoring. The GCF, greatest common factor, is always what you should look to take out first. The trinomials with a lead coefficient of 1 are the probably most common thing that you're going to be seeing, though we are going to be doing that similar method of grouping for when the lead coefficient is not 1. And then you also have some perfect square methods that are special. If you have a perfect square trinomial or you have a difference of 2 perfect squares or a binomial, you should be able to factor all of those now. So there are a few now you try problems that I'd like for you to give a shot.